All right, so we're going to kind of restart this topic of these Michaels reactions, but in a little bit more gory detail. We kind of looked at a specific case last time, so we can kind of get the format down, and now we're going to just be more detailed about it. All right, so we talked about our Michaels acceptors. Right? And again, these are compounds with electrophilic beta carbons. All right, we looked at a particular example last time, the enone. Okay, importantly, as long as we have this double bond conjugated to an electron withdrawing group, that will be a good Michaels acceptor. All right, we looked at a particular case last time where our electron withdrawing group was that carbonyl bond, but we could have a few other electron withdrawing groups that would work as well. All right, so let's just kind of put down a few examples. The vast majority of them are going to be carbonyl containing groups, right? So that electron withdrawing group could be an aldehyde, could be a ketone, could be an ester. All right, another one of our carbonyl containing functional groups that we haven't talked about too much are amides. We have a nitrogen on the other side of that double bond. All right, the only one that we're going to put on here and then mix out is a carboxylic acid. All right, it seems to meet that same criteria of all of our other electron withdrawing groups of having that carbonyl bond, but because of that acidic hydrogen, it's just not going to be compatible with these reactions. There are some other electron withdrawing groups, two other electron withdrawing groups that don't quite fit this same format. All right, the first one being a nitrile group. Again, we have carbon with a high order bond to a more electronegative atom, so these are also electron withdrawing groups. All right, and there's another really good electron withdrawing group that we introduced in our conversation about benzene derivatives, that nitro group. All right, so we looked at a very particular Michaels acceptor last time around. Truly, a Michaels acceptor is any time you have this pi bond that's conjugated to another electron withdrawing group, okay? And again, what that has the effect of is making this carbon right here, the beta carbon, a good electrophile. All right, so why is that? Let's look at our mechanism real quick. All right, we'll put in a particular electron withdrawing group. We'll just use our simple carbonyl group. All right, so if I have some nucleophile reacting with my Michaels acceptor here, All right, let's just remember our product. We're going to retain that carbonyl bond, that electron withdrawing group, but now we have our nucleophile added to that beta carbon. And this is kind of as far as we got last class, was kind of just looking at our products of these reactions, all right, where our nucleophile has formed a new bond with the beta carbon here, all right? So how does that work in terms of our mechanism? Well, our nucleophile is going to attack our electrophile, of course, all right, but carbon can't have too many bonds, so we got to get rid of this pi bond pair of electrons, all right? And because we have an electron withdrawing group, that electron withdrawing group is more than happy to accept those electrons, right? So why do we need an electron withdrawing group? To accept these electrons. Right, so at this point we have this. That pi bond pair of electrons has moved over, and we have a negative charge on that oxygen. All right, we have a name for these here. What are these in our alpha carbons chapter? It's an enolate. All right, and the next step will just be to protonate that enolate. We're going to use just water. I lied. We have our acidic workup, so we'll use hydronium. And at this step, I'm not quite at my product yet. All right, but again, we have a fancy term for these compounds right here, where the double bond is located right next door to that hydroxyl group. What are these? Not the enolate with the negative charge, but just the enols. And what do we know about our enols is that they are in this equilibrium that very much so favors that ketone product, our tautomerization. Right, so we need that really good electron withdrawing group on that Michael's acceptor in order to make that beta carbon electrophilic, right? It can then accept that pair of electrons to create that enolate ion. When we protonate that enolate ion, we just get an enol, but we know that enols are in this keto-enol tautomerization that very much so favors that keto product. So, again, we talked about Michael's acceptors last time, but we looked at a very specific example. Now we're going to kind of generalize this to anything that has this pi bond directly next to a good electron withdrawing group. All right, now let's talk about our Michael's donors. All right, what our Michaels donors are all going to have in common is that they are super stabilized carbanions. All right, we took a look at one specific one. We kind of used this to introduce these new organometallic compounds, these Gilman reagents. Gilman reagents are a lot like Grignard reagents. They make a new carbon-carbon bond, that organometallic compound, all right? But how I think of Gilman reagents, they're kind of like weak Grignards. They are nowhere near as nucleophilic as a Grignard because it just turns out that that carbon is much more stabilized with that negative charge, right? And again, this is going to be a common feature of all of our Michaels donors. All right, and this one was kind of an aside. Most of our Michaels donors is going to have this very characteristic feature of an alpha carbon sandwiched between two carbonyl groups. Right, so kind of the simplest example would be this propane dial here. All right, if this alpha carbon gets deprotonated, that negative charge is now stabilized, not by just one, but two carbonyl groups on either side, right? So this is a particularly stable enolate ion right here, right? That negative charge is stabilized even more than a regular aldehyde or ketone. And this is a common feature of a bunch of different Michaels acceptors, is to have that alpha carbon sandwiched between. It doesn't really matter if they're aldehydes or ketones or esters or whatever it may be, right? We can put down a bunch of different examples. Okay, they don't have to be symmetric. Make one side an aldehyde, one side an ester, whatever it may be, right? The bottom line is you have this alpha carbon that is sandwiched between two carbonyl carbons, so we get this extra stabilized carbanion. All right, just one more to note here, because again, it looks kind of different than these. Nitriles are just often lumped into the same category as carbonyls because they behave very similarly. Again, you have this high order bond to this more electronegative element. There's one more we're going to kind of put up at the top here because it's a little bit different in format. All right. And that is, it turns out that those nitro groups are just such good electron withdrawing groups that even if you just have one, that's enough to super stabilize that carbanion. Okay, so our common feature of these Michaels donors is that they are these super stabilized carbanions. Turns out they have to be relatively weak nucleophiles. All right, and let's just make note here. If we have too strong of a nucleophile, so for example, a Grignard reagent with the MGBR, or just a regular old enolate ion without being stabilized by two carbonyl groups. These are too strong of nucleophiles. And so even if we present a Michaels acceptor where have we seen Grignards react before in a molecule like this? What's the electrophilic site that Grignards, we've seen Grignards attack before? The carbonyl carbon, all right? And that's exactly what's going to happen. If we were to use too strong a nucleophile will react with our carbonyl carbon instead of our beta carbon. So that wouldn't be a Michaels reaction. You wouldn't be specifically targeting that beta carbon. Cool? All right, so Michaels reactions, on the one hand, you're just drawing a new bond between your nucleophile and your beta carbon, but look at these nucleophiles. Look at how big and ugly they are, right? So part of what makes these so complicated is really not the reaction itself, but just your reactants, yet you're combining, you're making this big product, it's got a bunch of carbonyl groups. It's just kind of hard to keep track of what's what, right? That's going to be the real challenge here. All you're doing is drawing a new bond between your nucleophile and that beta carbon, right? But keeping track of all the other crap is the hard part here, all right? So let's just take a look at a specific example. We'll kind of start simple and then build up. All right, we're just going to do a bunch of Michaels reactions. All right, so step one, let's take a Michaels donor. All right, this is a good candidate here because I have my alpha carbons sandwiched between two carbonyl groups. All right, but how do I actually turn this thing into a nucleophile? What am I going to have to treat it with? Some base, yeah, exactly. And actually, we can get away with a fairly weak base compared to what we were talking about before. LDA, complete overkill, right? This thing is a way better acid because that alpha carbon is sandwiched between two carbonyl groups. We can get super efficient with just something simple like NaOH. All right, we can do just regular old strong base. We don't have to go to our super strong organic bases. It's just a way better acid because of those two carbonyl groups. All right, but step one, we got to turn it into a nucleophile. Now we're going to add in our Michaels acceptor. All right, we'll use an enone for this example here. All right, and the last step for all of these reactions is going to be this acidic workup to protonate that enolate that you get. All right, so everybody take a second and see if you can't give me my product of this reaction here. So we need to identify our nucleophile, my alpha carbon of my Michaels donor. My electrophile is that beta carbon. All right, we're going to draw our new bonds. I'm going to start by redrawing that donor. Right, here's my new bond. So if this was my red carbon, that means my blue carbon has to be on the other side here. Okay, so then I'm just going to draw everything that's around that, including that retained carbonyl group of my Michaels acceptor here. Okay, and just like always, we're going to double check by counting carbons. All right, there were 3 carbons in my donor, those 3 there, and there were 4 carbons in that Michaels acceptor. Okay. So we got the alpha carbon of our donor connected to the beta carbon of our acceptor. All right, let's do another one, but just kind of use bigger and uglier things here. If we're starting out with an ester, remember we want to be kind of clever about our choice of base. We're going to use a base that matches that ester. So I'm going to use one of those methoxide ions or sodium methoxide. All right, we need to treat this. Let's go again, just a little bit more carbons. A different electron withdrawing group. Okay, again, we got that acidic workup. So again, I need to draw a new bond between my nucleophilic alpha carbon and my electrophilic beta carbon. Okay, I'm going to start by redrawing that nucleophile. This down. Okay, I'm going to form a new bond with my electrophile here. Importantly, I'm going to lose that carbon-carbon pi bond in the process. Probably point this down or give myself a little bit more room. Cool. So you don't really have to do, but just to space things out, right? I just kind of rotated about that bond to space things out. If you left it like this, that's perfectly fine too, okay? I guess I do need to include my lone pairs to be good. Cool. All right, so our Michaels donors are going to be these super stabilized carbonyl groups. I'm sorry, alpha carbons, super stabilized carbanions. There we go. All right, and so a typical feature is they're going to be sandwiched between two carbonyl groups. An alpha carbon that when deprotonated will be very stable as an enolate ion. We also have these other two kind of weird ones here. Our Gilman reagent, which is another just very stabilized carbanion organometallic compound. Or we can have just one nitro group instead of two, because nitro groups are just such strong electron withdrawing groups. Any one of these would be a good super stabilized carbocation that would react specifically with the beta carbon of a Michaels acceptor. Okay. The only thing, one more example that I want to do here is our Michaels acceptors, or at least the one up top here, these enones. These are actually the products of a reaction that we studied earlier, our aldol condensation reactions. All right, so this is just going to be a very easy way that we can piggyback two reactions. All right, what happens with acetone when I introduce some base and some heat? What is my product here? So remember, for these reactions, it might be more helpful to draw two molecules, since one of your acetones is playing the role of the nucleophile at its alpha carbon, and the other is playing the role of the electrophile at its carbonyl carbon. Right, so after that NaOH step, these are all combined together, but just to kind of show our intermediate here. This would be our aldol addition product. All right, but since there was heat in that reaction mixture as well, what's going to happen to my addition product? It's going to turn into a double bond. I'm going to have this dehydration reaction where now I get a conjugated double bond, or rather a pi bond that is conjugated to my original carbonyl group, right? Since we have heat, this is our condensation product. All right, and again, what I'm trying to point out here is notice that this condensation product has exactly the features of a Michaels acceptor. So if I were to take some Michaels donor, turn it into a nucleophile, and then add in that condensation product. All right, everybody take a second and give me the product of this reaction here. so again, I need to link that alpha carbon of my donor with that beta carbon of my condensation product, my Michaels acceptor. All right, so I'm going to have this draw this new carbon-carbon bond. On the other side has to be my electrophile. All right. It's going to still have that carbonyl group, right? That carbonyl group gets retained in these reactions. All right, but now it also has not one, but two methyl groups sticking off of there. All right, so again, my kind of just point was to point out here that our aldol condensation products are indeed Michaels acceptors. So we could take the product of that condensation reaction and turn around and introduce one of those super stabilized carbanions, and we would get these Michaels reactions where that nucleophile is added specifically to the beta carbon in that aldol condensation product. Cool. All right, we got one more topic to cover here. We're going to kick that can down the road until Friday, and where we'll talk about our Robinson unalation reactions, and that kind of closes it out for alpha carbon chemistry. All right, cool. So yeah, we'll cut it early today, and then we'll start in on that next class.